More than 95% of the universe is invisible. We can't see it, we can't touch it, but we know it's there, from the way galaxies rotate, from how light bends through space, and from the accelerating expansion of the cosmos. We've given it names: dark matter and dark energy. But what if these mysterious forces are more than just unknown substances? What if they're manifestations of something far stranger, something like tachyons? Let's explore the possibility that tachyons, faster-than-light particles with imaginary mass, may help explain the darkest parts of our universe. First, a quick review. Dark matter makes up about 27% of the universe. It doesn't emit light or energy, but exerts gravity, keeping galaxies together when visible matter isn't enough. Dark energy accounts for about 68%, and it's pushing the universe apart, accelerating cosmic expansion in ways we still don't fully understand. So where do tachyons come in? Some theoretical physicists have proposed that tachyon fields, scalar fields containing faster-than-light components, could behave like dark energy. Here's how. In string theory and quantum field theory, when a field is unstable, it can roll down toward a stable vacuum. This rolling process releases energy and can act like a negative pressure field. That's exactly what dark energy seems to be. One popular model is the tachyonic scalar field, a slowly evolving field with negative pressure. As it decays, it drives expansion, mimicking the effects of a cosmological constant. This idea gained traction in the early 2000s, especially as observations from WMAP and Planck confirmed that dark energy behaves like a constant but might be slightly dynamic. Tachyon fields fit the bill. They can be stable, slow-rolling, and still contribute to accelerated expansion, all without violating known laws of physics, as long as the tachyons don't transmit information or cause paradoxes. But that's just dark energy. What about dark matter? That's trickier. Dark matter clumps together. It forms halos around galaxies. It behaves like invisible mass. Tachyons, on the other hand, are repulsive. Their energy-momentum tensor behaves oppositely to normal matter. So, are they completely unrelated? Not necessarily. Some hybrid models propose that tachyon condensates, collections of tachyonic fields that decay into stable states, may leave behind topological defects or exotic remnants that interact only gravitationally. These remnants might behave like dark matter, clumping, bending light, and forming structure. In brane world scenarios, where our universe is a membrane in a higher dimensional space, tachyonic interactions between branes could lead to localized energy zones that resemble dark matter. Even more radically, some physicists propose that dark matter and dark energy aren't separate things, but two phases of the same underlying tachyonic field, acting differently in different cosmic regions. In this unified dark sector model, the tachyon field evolves over time. In some places, it creates gravitational attraction, dark matter-like effects. In others, it causes repulsion, dark energy-like acceleration. This would be an elegant solution. One field, two behaviors, governed by local conditions. Of course, it's still theoretical, but it gets even stranger. In certain string-inspired cosmologies, the entire early universe may have been dominated by tachyonic energy. This pre-Big Bang phase, sometimes called the tachyon-dominated era, would be a universe driven by instability, rolling down the vacuum landscape until it settled into the universe we see now. If true, then dark energy is not just a present phenomenon, but a lingering echo of our origin story. The slow decay of that early tachyon field may still be ongoing, pushing space outward. That would mean we're not just surrounded by tachyon energy, we are its consequence. But how could we ever know? Detecting tachyons directly is next to impossible. They don't interact via the strong, weak, or electromagnetic forces. but we might infer them indirectly. For example, unexplained fluctuations in dark energy's behavior over time, variations in the cosmic microwave background that can't be explained by standard inflation, tiny gravitational lensing anomalies inconsistent with particle dark matter. If these patterns match the predictions of tachyon field models, it could be the smoking gun. Furthermore, experiments like the Euclid Telescope, the Vera C. Rubin Observatory, and the James Webb Space Telescope are gathering unprecedented data about dark energy and dark matter distribution. We may soon discover inconsistencies, cracks in the standard model that point toward a new kind of field, a tachyonic fingerprint hidden in the cosmic code. Of course, many scientists are skeptical. Some argue that invoking tachyons overcomplicates the issue, that simpler explanations will do, and they may be right. But if we want to truly unify cosmology with quantum theory and string physics, we may need to embrace the strange. Tachyons may not be figments of science fiction. They may be the foundation of dark reality, not particles that violate causality, but fields that shape everything we see and don't see. So the next time you look up at the stars and wonder what's holding them together, or what's pushing galaxies apart, remember, it might not be matter or energy in any traditional sense. It might be tachyons, whispering from beyond the light.